Hey folks, how y'all doing? Um, we started reviewing for exam two on Monday. We're going to finish this up here. Um, let's go ahead and get started. What was JN25? JN25 was a diplomatic encryption system. Um, encryption used by the Japanese during World War II. Um, JN25 used a pair of books. One book converted um, individual words to 5-digit numbers. And then one of them just included just a list of shifts. Um, and so what would happen is if you had a message, you would convert each word in that message to a 5-digit number. Then you would go into your list of shift amounts, pick a random page, say, I am starting on page 22, and then shift each 5-digit number by the next amount on that list so that any recognizable 5-digit numbers would get shifted, and the shift amounts were all different because each word got shifted by a different amount. This book got replaced every 3 months. Um, and unfortunately, it took the American side about a month to crack the book. And so we had, these little cycles where we could decrypt messages and cycles where we couldn't. And Pearl Harbor took place during one of these cycles. Pearl Harbor took place 6 days after the JN25 shift books got replaced, and so we would have not had enough time to discover the shift amounts in those books. So um, anyway, that's what JN25 was. It was a diplomatic encryption that was done by hand. It was slow, but it was um, you know pretty good as encryption goes. It took us a month to break each book, and um, just those books had to be replaced after they got broken, and it took a while to develop and print and distribute those new books. So the advantage it gave us was, well, we had about 2 months out of every book that we could decrypt messages out of them. But the Japanese could time their major initiatives with the replacement of those books, and so the advantage we got was somewhat muted because of that. Anyway, let's move on. What are some of the differences between Enigma and Purple? Enigma was portable. That's a big thing. Purple was very heavy. Um, and so it was very difficult to move the Purple machine because it was not as portable. You could um, pick up Enigma, and I mean it wasn't light, but it was still you could pick it up and move it. So uh, the portability of Enigma was an advantage. Enigma used the rotors, and Purple used switching mechanisms. Um, Enigma only generated um, proper involutions. Purple generated actually more complicated permutations in some respects because they weren't involutions at all. But because of the 620 split, we knew part of the cycle type every single time. Um, so this did not generate involutions at all. Um, that made it harder to decrypt a message because decryption and encryption weren't the same process. Um, but that, like I said, increased the security in some respects and decreased it in others. So they had different goals in the way the encryption worked. So those would be, I would say, some of the major hardware differences between the two of them. The portability of the machine, the reliability. So the rotors were um, easy to replace. The switching mechanisms were difficult to replace, and so maintenance on the purple machine was hard. So this was heavy. It was also hard to maintain, and it was a little harder to decrypt messages with it. So purple was a more complicated device, and that complication did not necessarily lead to more security. So what was the 620 split was that that the purple settings for each day sent 20 letters of the alphabet through a an encryption process that, because of the changes in the switching mechanisms, would change the encryption every time you hit a letter. And so if you M was one of the letters that was one of the 20 letters that was going through this, every time you hit an M, it wouldn't encrypt the same way each time. Through a rotating encryption, but it sent 6 letters through a simpler fixed encryption. It wouldn't be, so when I say fixed, it's fixed for that day, um, not permanently fixed. Um, and this is because the switching mechanisms were originally designed to work with numeric data, and so there were 10 switch positions on each switching mechanism, and they were being used in pairs, um, which got up to 20 switch positions. But they didn't put in a third one, mostly because the machine was already heavy to begin with. And so increasing the number of switching mechanisms by a factor of 50% would have made the machine even heavier. So they stopped at 20, and then that meant that 6 letters each day got sent through a different type of encryption that was easier to break. Um, but once we broke these 6 letters, then well, 6 letters is almost 25% of the alphabet, and so we've got a definite foot in the door towards being able to then decrypt the other 20 letters. All right. So let's talk about the differences between confusion and diffusion and how they relate to perfect secrecy. Um, so confusion means that the relation between um, the key and the message should be sort of difficult to figure out, so that um, how do I want to explain the difference between these two? Um, so if we have a message, and let's say it's just a series of bits, so if the plain text has a 0 in a position, the ciphertext, we should not be able to easily predict whether the ciphertext will be a 0 or a 1. That is, this should be happen about 50% of the time, and this should also happen about 50% of the time. But the 50% of the time should not be dependent on like recognizing a pattern in the keys, so that uh, so that uh, in other words, knowing the ciphertext doesn't tell me what the plain text is, because half the time it's going to be one, half the time it's going to be the other. Um, but that this shouldn't be closely related to a pattern in the keys. But this shouldn't be easily predicted based on the key. So as an example, just a simple XOR operation doesn't cause much confusion, because if I XOR with a 0, I know exactly what I'm going to get. If I XOR with a 1, I know exactly what I'm going to get. There should be something more complicated than just an XOR operation, so that knowing the plain ciphertext doesn't give me some insight onto how the key might have worked. So that at any excuse me, at any place within the message, the odds of having a particular bit is roughly random and not heavily correlated to whatever the key is at that position. So that's the idea. So what a diffusion is that if we have, say, two plain texts, they are identical except in one position, where one plain text contains a 0 and one plain text contains a 1. So they're identical except in one place. Then the ciphertext that we should get shouldn't just differ in that one place, because then that would give me a clue as to where the difference is. The ciphertext should differ in multiple places throughout the ciphertext, so that the alteration of the plain text somehow spreads out and alters the ciphertext in multiple places. So a change in the plain text propagates to multiple places in the ciphertext, so that we can't, by identifying changes in the ciphertext, locate where the change in the plain text was. That's the idea. Okay. Perfect secrecy is that is that the probability of any particular plain text given the ciphertext is exactly equal to the probability of that plain text. That is, that knowing the ciphertext does not alter the probability of any particular plaintext. And so the ciphertext cannot give away any patterns about the confusion and diffusion. In practice, this is impossible to achieve in practice. There are theoretical ways to do this, but the applying that theory to practice becomes impractical because it requires memorizing a key that is the same length as the plain text, for example. That's if you're going to have that much data memorized, you may as well just memorize the message. So this is impractical. But each of these helps to make this an approximation. So that confusion and diffusion at least make it the case that the probability of a plain text given a particular ciphertext is approximately equal to the probability of a plain text. And in fact, for AES, this approximation is very good. So AES gets very close to this. That's sort of the important thing. That we want to approach perfect secrecy using something that is practical. All right, let's move on. Describe the general structure of an SPN. So the general structure includes some rounds. So where we start a round and we do a sequence of substitution operations. Followed by a sequence of permutation operations. So this is what creates the confusion. This is what creates the diffusion. Confusion is we're making substitutions that are essentially random, but not entirely random. They're based on some table where the table was generated randomly. And then the permutation then rearranges things so that the errors are propagated or the changes are propagated to different places in the ciphertext. There may be some additional steps. Often there is a key step in here where we do some XORing with the key. But strictly, that's not necessary for an SPN. An SPN just does a combination of substitution, permutation operations. That ends the round, but goes back through here and does multiple rounds, except in that there's a final round that's slightly different. Where if we're going to do an XOR operation, we do it at the beginning of the round. We complete the substitution steps, but we skip the permutation steps in favor of a second XOR. So that's the idea, that the substitution creates confusion, the permutation helps to create diffusion. And we go through these multiple rounds, but the final round is a little bit different. Here's the reason why the final round is different. Let me write out, let's say we did 5 rounds. So if we did 5 rounds, then what we would have is an XOR step, followed by a substitution step, followed by a permutation step. That's round 1. Then an XOR, then a substitution, then a permutation. That's round 2, round 3, round 4, and then round 5 is an XOR, then a substitution, and then an XOR. We have a theorem that says that an XOR followed by permutation is equivalent to a permutation followed by, or a permutation followed by an XOR is equivalent to an XOR followed by permutation, but these keys are different. That is, we could switch the order of a permutation. We just have to change the key around. And so if this is what we do to encrypt, then decryption would be to go through this in reverse, which is X, S, X, P, S, X, P, S, X. Let's see, how to do 1 round, 2 rounds, 3 rounds, 4 rounds, 5 rounds. But then if we apply this theorem that says I can take these XPs and reverse them, then I get XS, then PX, S, then PX, S, then PX, S, then PX, SX. And that's exactly the same as the encryption process, just using different keys. And so in an SPN, it is possible to use the encryption function to decrypt messages, just using a different set of keys. And so that simplifies the amount of code that has to be generated in order to make an SPN work. That's the idea. Okay? So how does decryption work in an SPN? Well, we just talked about that. Decryption uses the same process as encryption, but using a different key schedule. So same as encryption, but using different keys. Why can the order of a permutation step and an XOR step be inverted? All right. So let's look at this. If we have some plain text and we do an XOR and then we do a permutation. So we have our plain text is X1, X2, X3, X4, X5. Let's just say just that. And then we have a key 1, key 2, key 3, key 4, key 5. Then we XOR them together and we get, I'm going to move my permutation down so I've got some space here. So now this changes these bytes around to, let's say Y1, Y2, Y3, Y4, Y5. And then we permute them into some order, let's say Y5, Y4, Y3, Y2, Y1. And so this is what comes out. So if we want to invert that, so instead of permuting and then XORing backwards, we want to still be able to do an XOR and a permutation. Then we want the permutation to end up with X1, X2, X3, X4, X5. But the permutation does this backwards. So this permutation reverses the order of elements. So after the XOR step, we had to come out with X5, X4, X3, X2, X1. But that means the XOR step would have K5 at the beginning, and then K4 here, and then K3, then K2, and K1. And so this key and this key are different, but the relationship between these keys is the relationship of the permutation. And so if we put the permutation onto this key so that the order of the bits in the key get reversed, then we're XORing things in the right order so that we can then permute everything back and get our original plaintext back. That's the idea. And so if we apply the permutation to the original key, then we can use the permuted key on the ciphertext, and then we can get the plain text back by doing an XOR and a permutation instead of having to do a permutation and then an XOR. All right. So perform addition and multiplication in this field. So addition is the same as XOR. So if we have 2 bytes, 7, 3, B, and 2. So 7 is 1, 1, 0, 1, 1, 1, 0, 0, 1, 1. B is 1, 0, 1, 1, and 2 is 0, 0, 1, 0. We add them together, we get 1, 1, 0, 0, 0, 0, 0, 1, and that is C1. Okay? Multiplication is trickier. If we were to do this again, 7, 3 times B2, then what we end up getting is a very long polynomial that we would have to then reduce. And so multiplication, if we do this using long division, this is what we get. So multiplying it by this one gets me 1, 1, 0, 0, 1, 1, 1. Everything shifts to the left one place. Then multiplying by this one gets me 0, 1, 1, 1, 0, 0, 1, 1. Then multiplying by this one gets me 0, 1, 1, 1, 0, 0, 1, 1. And then multiplying by this one gets me 1, 1, 1, 0, 0, 0, 0, 1, 1. Sorry, just 2 zeros there. All right, and then when we XOR all these together, we get 1, 1, 0, 0, 0, 0. All of those are zeros, it turns out. 0, 0, 1, 1, 0, 1, 1, 0. Okay. Well, that is 14 bits long, and we need to reduce it down to 8 bits long. And so we do this by dividing this polynomial into this polynomial and getting the remainder. And so 1, 0, 0, 0, 1, 1, 0, 1, 1 into 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0. There we go. Oh, let's see. So this goes in once. We get 1, 0, 0, 0, 1, 1, 0, 1, 1. And that reduces down to 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0. Go one more time. 1, 0, 0, 0, 1, 1, 0, 1, 1. And that gives me 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0. That's still too big. So then we get 2 zeros and a 1. 1, 0, 0, 0, 1, 1, 0, 1, 1. And that leaves me with 1, 1, 0, 1, 0, 0, 0, 0. And that fits in a byte. That is the byte D0. And so we get our answer by doing multiplication followed by long division. The other way we can do this is to do multiplication using x time. So we start with 7, 3. 7, 3 times 1 is just 7, 3. 7, 3 times x is x time of 7, 3. So that's, we're going to take this byte and we're going to shift it over 1. 1, 1, 1, 0, 0, 1, 1, 0, and that turns out to be E6. And then 7, 3 times x squared is x time of E6. So that's got to be this shifted over 1 time again. 1, 1, 1, 0, 0, 1, 1, 0, 0. But that's too big to fit in a byte, so we XOR it with 1, 0, 0, 0, 1, 1, 0, 1, 1. And that gets us 1, 1, 0, 1, 0, 1, 1, 1. That is D7. So then 7, 3 times x cubed is x time of D7. So that's this byte here shifted over 1. And then XORed with the AES polynomial, and we get 1, 0, 1, 1, 0, 1, 0, 1, and that is B5. So then 7, 3 times x to the 4th is x time of B5. So we left shift this again, 1, 0, 1, 1, 0, 1, 0, 1, 0, XORed with 1, 0, 0, 0, 1, 1, 0, 1, 1. And we end up with 0, 1, 1, 1, 0, 0, 0, 1, which is 7, 1. All right, I'm starting to run out of space over here, so I'm going to go back over here and finish this up. 7, 3 times x to the 5 is x time of 7, 1. So that's 1, 1, 1, 0, 0, 0, 1, 0, which is E2. 7, 3 times x to the 6th is x time of E2. So that's 1, 1, 1, 0, 0, 0, 1, 0, 0, XORed with the XOR polynomial, which is, or the AES polynomial, 1, 1, 0, 1, 1, 1, 1, 1. So that is DF. And then 7, 3 times x to the 7th is x time of DF, which is 1, 1, 0, 1, 1, 1, 1, 1, 0, XOR with 1, 0, 0, 0, 1, 1, 0, 1, 1. And that's 1, 0, 1, 0, 0, 1, 0, 1, which is A5. All right. So now we have this table of 7, 3 times different powers, but B2 is, so B2 is x to the 7th plus x to the fifth plus x to the fourth plus x, oh, just x. So 7, no 6, 5, 4, no 3, no 2, x to the first, and then no 0. And so 7, 3 times b2 is going to be 7, 3 times x to the seventh. It's going to be a5. And then x to the fifth is e2. Then times x to the fourth is 7, 1. And then times x is e6. And then we would XOR all of these together, and that would get us, well, it should get us the same result. We should end up getting D0 when we're done. Okay? So that's how we do this using xtime. We apply xtime recursively to build up this table of 7 3 times different powers of x. Then we list those powers that are in B2, and we multiply 7 3 times all of those powers and XOR them together. All right? So then show how to find the inverse of a polynomial in this field. So let's just go ahead and keep using 7 3 here. So we want to find 7 3 inverse, which is 0 1 1 1 0 0 1 1 inverse. So what we're going to do is we're going to divide this polynomial into AES. This is our AES polynomial. All right, so this is x to the sixth, this is x to the ninth. So we're going to get x cubed. And that's going to take us 1 1 1 0 0 1 1. My bad, this is x to the 6th, this is x to the 8th, so this is only going to be x squared. I've got one extra position here. That's okay. All right, so then we're going to XOR these, and we get 1 1 0 0 0 1 1 1. All right, this is x to the 6th, this is x to the 7th. That goes in one time. 1 1 1 0 0 1 1. And we're left with 1 0 0 0 0 1. This has a smaller degree than this does. And so this goes in no more times. And so now we're going to divide 1 0 0 0 0 1 into 1 1 1 0 0 1 1. That's going to go in one time. And we're left with 1 1 0 0 0 1. When we divide that a second time, we're left with 1 0 0 0 0. This is shorter than this. It's got a smaller degree. And so we stop dividing and do this one. So this is easy. This goes in one time. And we're left with 1 left over. And then, so this doesn't go into 1, but 1 goes into this. X to the 4th times. And that leaves you with the remainder of 0. So we stop when we get to a remainder of 0. The fact that we ended up with a 1 before we got to a 0 tells me that this is invertible. That's good. And so what we're going to do now is do the extended part of the algorithm. So 1 times 1 1 0 is 1 1 0. And 0 XOR 1 1 0 is also 1 1 0. So that's got to be what goes over here. So then we use this number and then these two numbers here. So 110 XOR multiplied by 11 is that's 110 and 110. So we get 1010. But we have to XOR that with 1. So 1 XORed with 1010 is 1011. That's the number that goes here. We multiply these two together and then take the number that's on top over here and XOR it. So 1011 multiplied by 10 is just 10110, and 110 XOR with 10110 is 10000. So that's the number that goes over here, and that last number is the inverse. All right. So that turns out to be the inverse. The inverse turns out to be the byte 10, which is in bits 10000. All right. Sounds good. Let's move on. Describe these parts of the AES encryption standard. So add round key is the XOR step. But it's a different key for each round. And so the add round key, first of all, makes a call to the key scheduler and says, give me a key that works for this round. And then whatever key it is, it XORs the text from the previous step with that key. So it's a different key each round. The sub-byte step is just a lookup table. We're going to take an 8 bits and replace it with 8 different bits. So 8 bits in, 8 bits out. But we're making a substitution of 8 different bits for the other ones. This table has 256 rows, and each row has an input and an output. And so that's way too much information to memorize. You should never feel like you have to memorize the sub-bytes table. Shift rows, we're going to take 16 bytes and put them in an array, a 4x4 array. And then we're going to rotate the rows by different amounts. So we rotate the top row by 0, which doesn't do anything. And then the next row by 1, and then the next row after that by 2, and then the bottom row by 3. That rotation is one of the ways that we're creating some diffusion. We're taking errors in the message or changes in the message and moving them into different places in the message by rotating the bytes in these rows. And then mixed columns, I've not given myself room here to work on that. But mixed columns is a multiplication step. We have this matrix that's part of the algorithm, and we will multiply it by the columns that we come out of the shift rows. And then we end up getting new columns, and that will be the matrix that we pass on to the next round. And then finally, key expansion combines an XOR, a substitution step, and a little bit of rotation. But the XOR schedule is simpler here because otherwise we would have to have an expander for the key expansion routine instead. So this is a simple XOR. This is a more complicated XOR in terms of what's going on. All right. So we'll look at each of these parts in much more detail after the exam. What are the block size, the key sizes, and the corresponding number of rounds for AES encryption? The block size is 128 bits. And then your key sizes, you can choose. If you're encrypting a message, you can choose. If you're decrypting, you have to decrypt using the same standard that the encryptor used. But 128, 192, or 256 bits. And each of these takes a different number of rounds. And so this encryption would take 40% longer than this encryption. Because it uses, 4 extra rounds. And so we have 3 different layers of security. And so far, even the easiest layer, the 128-bit layer, hasn't been broken yet. So none of these have been broken, but we gain additional security with a longer key size and more rounds. But there is a time consideration as well. If we have to encrypt a large number of records, then that extra, increasing the amount of time by a factor of 40% can turn out to be significant. So different applications will take different layers of encryption here. All right. That's it for the questions that I've put on the practice sheet. If you have other questions that you want to ask about, I've got office hours at 3 o'clock on Thursday. I'm happy to go over them with you. If you're looking at this video for the first time on Friday, I will be in class on Friday. Why don't you come on by and ask questions there? I'll talk to you later. Take care.